Okay.
Can you just say a few words? Sure, son.
Hi.
Okay,
Oh.
great. Okay. All right, welcome everybody. Let's get started for this week. I am so excited to introduce our seminar speaker, Dr. Nicolas Stauff from Argonne National Laboratory. He's been with Argonne since 2012 and is now the manager of the Nuclear Applications and Economics Group, where he does a lot of research in fuel cycles, reactor physics, microreactor technology, advanced nuclear, and really a holistic view of how we can integrate nuclear with a clean energy transition. He also does a lot of work with microreactor technology development and has supported industry designs, including Westinghouse, HolosGen, and others. So I'm really excited to introduce Dr. Stauff. He has a PhD from Paris 11 University, other degrees from France as well. So please welcome our speaker and join me.
All right, thank you very much, and it's great to be back here. Last time was it's very loud, 6-7 years. So no, it was long due. Thanks a lot for the invitation, Professor Brook. And today I will talk about a recent study that we did on assessing nuclear energy capability to support negative emission technology. So it's relatively new topic. I think that DOE-NE got interested into funding, and the report just was released a month ago. But before I will start with a brief introduction of what we do in my group, a little bit of advertisement, and after that we'll start with that was wrong button. Okay, with this discussion on this project that was just released. So my group, Nuclear Application and Economics, so it fits into the Argonne Lab. I don't know if anyone has been at Argonne. It's one of the, it's a very large national lab, one of the 17 national lab funded that is led by Department of Energy, Office of Science. So it's a very broad area of research that we do. We have one of the fastest supercomputer in the world, one of the brightest neutron source here, APS. Lots of research in a little bit everywhere, energy and non-energy related, and we have a big nuclear energy, and I don't know why the E is not right, nuclear energy department. In fact, well, I'm not going to start with the history of Argonne in nuclear energy, but it's rooted in nuclear energy. So my group is Nuclear Application and Economics. Our motto is to contribute to developing safe and economical nuclear technologies to support a wide range of applications. Our main areas of expertise are in nuclear systems and energy markets economics, in advanced reactor design, and in modeling and simulation. And I will show you how these all fit kind of together with a few examples. So we have, wrong button again. On the reactor design analysis, we work with Westinghouse on their LFR project, work with Natrium on reviewing some of their safety documents. We work with some micro-reactor design. We've done some work for industry and for DOE, for instance, with high fidelity modeling of different micro-reactor designs. On techno-economics analysis, a wide range of activities from energy market modeling, looking at how much nuclear reactor need to be deployed to ensure reliability of the US grid. We look at cost estimate. That's a project I'm going to be discussing, cost estimate of nuclear projects and market compatibility for advanced reactors. And finally, a very big topic here, which is estimating schedule and cost of transportation of spent nuclear fuel with different scenarios of nuclear waste storage projects. And finally, modeling and simulation. we are, my team is developing different tools for like user interface for some neutronic tools, workflow management tools for linking all these different tools and capability, cost estimate tools for capital cost estimate, fuel cycle analysis, and energy market modeling. For instance, ABC, that's an agent-based capacity expansion tool that will be able to model utility decision to deploy different types of reactor technologies. So that's it for brief introduction of my team. Now I'll go to the more technical talk on nuclear energy compatibility with negative emission technologies. I want to start by acknowledging all the co-authors of this study from Argonne, INL, and especially NETL. And the report is available online. So why negative emission technologies? So first, according to the IPCC, there will be a need. It's said with high confidence there will be a need for negative emission technology or carbon dioxide removal technologies to counterbalance hard to abate residual emissions if we want to achieve a net zero emission system, which will be needed to reach 1.5 degrees Celsius, to limit global warming to 1.5 degrees Celsius. And we know that we need to remove almost 400 or 700 billion ton of CO2 to limit warming to 1.5 Celsius, and that's 5 to 10 million ton of CO2 per year between 2040 and 2100. That's big numbers, but it's difficult really to know how difficult that will be. So I'll through my discussion, hopefully you will see how many, for instance, nuclear reactor you need to deploy to get to such numbers. So nuclear energy, already is a big contributor to help not put extra ton of CO2 to the atmosphere by providing clean electricity production. And hopefully in the future we can use nuclear reactor also to produce to use it to power some other industrial application, some university campuses maybe. But maybe so what we wanted to see here is that could we see another future application for nuclear energy beyond electricity, beyond industrial application on other niche markets, to support some negative emission technologies? So that's what I'm going to be talking about. So first, let's review some negative emission technologies. So here I'm going to be mostly talking about nuclear energy, negative emission technologies that require a source of energy that the man can provide to remove CO2 from the atmosphere. There are other type of negative emission technologies like reforestation or land management that won't need nuclear energy. So the first one that is that a lot of people talk about whenever we talk about carbon removal is DAC, direct air capture, which typically is associated with carbon sequestration, so that once we have removed CO2, so it's a chemical process that captures CO2 from ambient air and then concentrate it, and afterward we're going to store CO2 in geological reservoirs so that we can achieve this negative emission. So that's one system we've been looking at. There are other systems like biomass-based system where the plant, when growing, will capture CO2 from the atmosphere, and then we burn trees, or we burn it, or we go through some process of pyrolysis, of gasification to extract the carbon out of it. And so in one way, when we burn it, we produce electricity, and then we can separate the CO2 and send it underground. That's one biomass process. The second one is pyrolysis or gasification, where we'll burn CO2 at very high temperature, and we'll extract biofuel, other solid materials and gas, some CO2 that we can put underground, and other hydrogen and other results. So this is biomass process. I think will be an important role also is an important type of negative emission technology. Water-based process are also very interesting. There are different types again of water-based process. One is enhanced weathering. It's a chemical reaction to store ambient air, to store CO2, to capture CO2 naturally and store it in seawater. And as we store it into water. And the next one is seawater capture. So here, CO2 is extracted from seawater instead of atmosphere and stored in geological reservoirs. So this one makes sense because CO2 is more concentrated in seawater than in the atmosphere, so it requires lower amount of energy to extract from seawater. But then afterward, there is some type of equilibrium between the CO2 concentration on the atmosphere and seawater that will make sense to go through this process. But this is way less advanced, and I haven't seen it really make it into the type of IPCC scenarios. So it's really something early on in process, in development. And once again, other negative emission technologies are under development, but would not pair well with nuclear energy. So big table here. We just go through all these, direct air processes, biomass process, water-based process. Short description. I already described most of these. The most important here is that we characterize what type of heat will be required. All of them, most of them will require some form of heat and some form of electricity. Most of them require some electricity, some will require a lot, some will require a little bit. And then we document what type of product we get, how we store CO2. Basically here in DAC, we have concentrated CO2 that then needs to be sent underground. In others, like enhanced weathering, it's CO2 is dissolved in the seawater. In biomass process, here, for instance, CO2 will be stored in biochar, which is kind of a soil highly concentrated in carbon, and as bio oil, for instance, that could be stored also underground. So, but just a summary now. I have extra slide to talk more about some of these processes, but in this presentation, I'm really going to focus on the DAC system, which are the one that we could evaluate much further with nuclear energy. And we did a more detailed techno-economics type of analysis on nuclear coupled with DAC. So there are two DAC technologies that we considered. One is what we call liquid solvent DAC or LDAC. So in this case, CO2 is within the atmosphere. CO2 here are the purple dots here. So it's mixed in the atmosphere. It's being sent by concentrated. We have big fans that bring it in basically, and it reacts with KOH. Goes through a few chemical reactions. I'm not going to detail them much, but basically those are needed to those go to the calciner that will require very high temperature heat, typically provided by natural gas, to release the CO2, and then we have access to highly concentrated CO2. This is really how the LDAC works. Now, how could this pair with a nuclear reactor? First, you need a lot of electricity in these two steps of the LDAC process that could come from a nuclear reactor. And then you need high temperature heat. Typically, ideally, that could come from a very high temperature reactor, but it's a little bit beyond what a commercial reactor can do. So in our current study, we only considered it coming from natural gas, but in the future, we could look at having, nuclear heat used here, maybe with some reheater using electricity or less natural gas. So there are different options we'll be looking at, but right now we're only considering nuclear electricity here to power this process. The second technology, DAC technology, is called solid sorbent DAC or SDAC. So here it's relatively a simpler process. So we have the atmospheric air that goes through like a solid sorbent that will, like a sponge that will capture CO2 here. And you get depleted air out. And then you need to have high temperature steam go through this process to extract CO2 with your water, and then you can condensate it and extract the highly concentrated CO2. So in this case, you need electricity to power all these different stages here, but you also need high temperature steam in the 150 Celsius range, which is closer to what, it's within the range of every nuclear power plant. So here we have a good opportunity to leverage both electricity and relatively medium temperature heat from nuclear reactor. So let's talk about economic feasibility of this system. First, what are the output of a nuclear power plant? So I know I know you all typically will know this, but I think this is important to quantify what a nuclear power plant can provide. The first option would be to use a nuclear power plant to only generate high quality heat. Different nuclear concepts will be able to provide different types of high quality heat, and we'll be looking at that. Or it can provide some electricity with some high quality heat. So, or it can provide only electricity, or maximize its electrical output, and then you get some free waste heat. All reactors have a lot of free waste heat that can be made available. So in order to quantify how much of this can be made available, it's reactor technology dependent. So we looked at three main reactor concept types. A pressurized water reactor, that's traditional nuclear technology that is available, that is powering our grid. Then we have sodium cool fast reactor that will provide relatively higher type of temperature, and a very high temperature reactor, which are being considered also as so both are being advanced here through the ARDP demonstration project and have relatively near-term demonstration plans for large reactor and even for micro reactors. But for this study, we only looked at relatively, so we're not looking at one reactor technology in particular. We're looking at reactor types, and we are sizing them all at 1 gigawatt thermal. So for consistency of the study that we are doing, the techno-economic study. So in this table, basically, I provide what type of temperature is available from all reactor technology on the secondary side. So PWR around 270 Celsius, SFR around 500, VHCR around 850. What is waste heat temperature typically available? For PWR SFR, Rankine cycle, we're around less than 50 Celsius. For the VHCR, it's a direct Brayton cycle we were looking at. We're at around 125 Celsius. And then thermal efficiency here. So looking back at our three options here, if we want only to generate heat, then we will have these temperatures available with all of our outputs. So we know exactly the amount of, we have 1 gigawatt thermal of output at this temperature. If we are looking at, let's go to option 3, which is easier, which will be used for our nuclear coupled with LDAC, where we only use electricity from the nuclear reactor. So here we'll just maximize the electricity production. So we'll have 352 megawatt available from the PWR, because we have 35.2% efficiency. We will have 420 megawatt from the SFR, and we will have 446 megawatt from the VHCR. Now, for if we want to look more at generating some electricity and some relatively high quality heat, that's for my SDAC, where I need to have some steam at around 150 Celsius. So here we did kind of an optimization of our system to try to get as much as heat, steam at around 150 Celsius, and to be able to generate some a large amount of electricity. So we perform this optimization here, and so we've got both steam and electricity available for our DAC system. The next thing we need to ask is how expensive is going to be our nuclear reactor. Yeah. So here we're leveraging some work done under a DOE-NE campaign that has been working a lot on quantifying the cost of nuclear reactors, and we have data for both a PWR, an SFR, and a VHCR. So we're just leveraging this number. So we need, let me just mention this. We need an overnight capital, the capital cost here, OCC. VOM is variable operation and maintenance cost. FOM is fixed O&M, and fuel cost, obviously. Other assumption used, we are considering 90% capacity factor, 60-year lifetime for a nuclear reactor, 30-year for the DAC, 6.2 interest rate, and 5-year construction time. All right, now let's look at the cost of the DAC system. Starting with the LDAC system. So here, once again, nuclear reactor is only considered for electricity production. And so we use all the electricity produced by your PWR, SFR, or VHCR. And we use natural gas combustion to provide the 900 Celsius temperature here. Yeah. So what we found is that with our power here, if we were to use all our electricity available, then we're able to extract from 12 to 15 million tons of CO2 per year, which is not bad. Now we need 10,000 times more to meet our IPCC scenario goals. But it's already not bad. But that, as a reminder, you still need about natural gas combustion, about 2 gigawatts thermal of power for 1 gigawatt thermal of on the reactor side, on the nuclear reactor side. What is the cost of this system? So first, there is a big uncertainty. Such DAC system at this stage has never been really considered. So we have some good estimate of a 1 million ton per year, but a 10 million ton per year, it's really difficult to know how it will scale up. So basically, the expert at NETL that make this estimate provided us a range between let's have 10 1 million ton module, put one next to each other, or let's build a big one where we expect some economy of scale. So this is why, if we have economy of scale, your LDAC system will be, for PWR, will be only $5 billion. This is $1 million. If there is no economy of scale and we have to put them module by module next to each other, then this is going to be $13 billion. So the cost of the DAC is a little bit expensive. And yeah, this is a range, similar range that we have for all technology. As you can see, higher temperature will lead to more, electrical power from the nuclear power plant. So will lead to more CO2 that can be extracted, but then will lead to also more expensive DAC system, because we need just a larger DAC to be able to take all the electricity. And then even the operating costs are relatively high, almost $1 billion of variable O&M per year. So it's important to keep in mind those costs. Now, SDAC. The SDAC is a little bit less impressive, both in performance and in cost. So here, as a reminder, we are using nuclear electricity and low temperature heat. In this case, we can only store with our nuclear reactor about 1 million tons per year, but we don't need any natural gas in this case. One thing to bring out, in the VHTR, we're using all the heat from the VHTR that is available for free from our waste heat, all the electricity that we can, and we still have 42 megawatt electrical available to sell to the grid. What is the cost of the SDAC system? Just of the SDAC here. It's 1.5 to 2 million ton, to $2 billion for the capital cost, and the operating cost, fixed is not too bad. Variable is is quite high, around $300 to $400 million. Now, those are a lot of numbers, a lot of performance. We used an equation here to calculate the levelized cost of DAC. So that's a little bit easier to try to provide the number of, what is the cost of 1 ton of CO2 that is extracted from the atmosphere. So that's easier just to compare. And that includes the cost of the nuclear reactor. So for the nuclear plus LDAC system, where we can, once again, we can remove 12 to 15 million tons per year, the cost of per CO2 will be $170 to $260 per ton. So it's not too bad. The SDAC, because we have, even though the cost was less, the capture performance is less, and ultimately the cost of the CO2 captured will be around $600 to $700 per ton. So the SDAC technology seems a little bit less feasible, even though it takes more advantage of the nuclear reactor to provide both heat and electricity. All right. And yes, just to remember, we are getting some good amount of CO2 here that is removed, but it requires all the electricity from the nuclear reactor plus 2 gigawatt thermal of natural gas. How does it compare to non-nuclear DAC system? That's the most important follow-up question. So here we worked with researchers from NETL that initially did this analysis for non-nuclear DAC system. So they considered DAC powered by grid electricity and by natural gas. So we have this reference number in reports, and what we found is that, so here we have our 3 LDAC system, 3 SDAC system for 3 different types of reactors. Typically, it's not going to change significantly from one reactor to another. What we find is that we're in the same ballpark for LDAC, 5 to 7% less. We don't see it, and that's assuming here the modular assumption, which is more conservative. We are not leveraging any scaling of the DAC system, because that's not really going to be specific to nuclear. So we don't want to account for it. But we still have 5 to 7% cost reduction from using a nuclear reactor. For the SDAC, we have a little bit more, 8 to 13%, and that's mostly because we're we are better using the nuclear energy with both heat and electricity. Ultimately, with the nuclear reactor, we have a slightly more it's more capital intensive, so we'll have a little bit more capital cost, but less fuel cost and slightly less operating cost. What is a nuclear component in this cost? So here it's the same graph, but instead of showing the capital and operating cost, I'm showing the DAC component and the NPP and the nuclear component. What is interesting is that you think nuclear is expensive, DAC is really expensive. So you can see that even in the SDAC system, where we have a perfect match between a nuclear reactor and the SDAC system, the SDAC will still be a large part of the cost. Nuclear is only 30%. And that's very important to understand, because the main reason we have a cost reduction here is not that nuclear energy is cheaper to generate electricity and heat than natural gas. In fact, it's kind of the other way around. It's really similar, if not more expensive to generate it with nuclear energy. The main reason nuclear energy is more advantageous, provide a little bit of gain here, is because we don't have to compensate for emission from energy. If we're using natural gas, it means that we are releasing CO2 from the atmosphere that we are trying also to capture in this system. But still, we need to have a DAC system that will be 15 to 30% larger. That will be 15 to 30% more expensive in terms of capital and operating costs than when we use a nuclear reactor, a clean source of electricity and heat. That's really the main learning of this study. So who will pay for that? That's the follow-up question. What are the markets for CO2 capture? So we, in this graph, it's just the same here, but we are showing a bar here, the average and the kind of the range where we are. We have different markets available that are willing to pay for CO2 captures. The first one is enhanced oil recovery. It's basically the industry that wants to remove to get oil from the ground and sell it to us customers, and that are willing to pay for CO2 to be injected underground. It's only $30 per CO2, but it's not nothing. Then there is the US government with the IRA policy that is providing 130 to 180 ton per CO2 that is removed and stored underground. 130 will be when linked to the enhanced oil recovery. So here we're still lower than our nuclear with DAC, but we're not too far lower. And 180 here with just the tax rate. Then there are industrial applications like food industry and others, like potential synfuel industry that would require CO2. Those are emerging applications that could pair well with this type of processes. And there is a voluntary offset market. Those are big companies that want to pay money so that they can claim their net zero, they have a clean operation, net zero CO2 emission, that are willing to pay. And some are, we have seen some prices that are extremely high, and that could also combine with some of the tax credit here potentially. So basically, there are incentives out there. What is missing is certainty, but those are going to be available for the long term. All right, and that's my summary. Just I think the messages were pretty clear. A nuclear reactor would be able to store, when paired with DAC, 12 to 15 million ton with one technology, 1 million ton with another technology. It helps reduce, pairing it with DAC can help reduce the cost of CO2 capture by 5 to 13%. And higher nuclear reactor temperatures can provide improved performance if it doesn't come also with a higher cost of the nuclear technology, of course. But really, what is important is why nuclear is a good partner with DAC, because DAC requires electricity, large amount, base load, stable and low prices. And there's a lot to say here. Base load, because DAC is very capital intensive and will require base load operation. Stable and low prices, because it has, we want to make a case that we want a several $billion investment. So we need to have a good case for that. We require also large amount of heat with different quality temperature depending on the technology, but especially we need non-emission source of energy. And nuclear here provide a very good case. All right, and maybe I can leave this for discussion if you have questions. One thing that I want to mention is that would it make sense? One of the questions I receive typically, does it make sense to deploy this system now, or should we first decarbonize the grid or other applications? And you have to keep in mind that 1 gigawatt thermal PWR already avoid emission of around 1 million tons of CO2 per year. If it was, if it replaces a natural gas combined cycle plant. So I think it's definitely more advantageous to deploy a nuclear power plant to decarbonize the grid from natural gas when compared to a PWR linked with a DAC to compensate for this emission. So this, we have future work, but let me just mention that we have more information on our website. We have job postings for internship or staff positions, so feel free to look at these. And I want to acknowledge my co-authors and DOE. Thank you very much for your attention.